All right, welcome to the hackathon, everyone. Today, we're targeting a highly secure, high tariff system, the Cambridge 9709 mathematics mainframe. And specifically, we are cracking one of its absolute most notorious algorithms, integration and the volume of revolution about axes. It's wild. Every single year, thousands of students approach this syllabus like it's just a simple calculator exercise. And every year, their code completely fails to compile when those final grades are outputted. So we're going to change that. We are going to treat this complex, multi-part problem exactly like an algorithm, one that can be solved with precise code-like syntax. Let's get to work. Okay, let's dive into this. Why are so many genuinely brilliant candidates facing these critical system failures the second they hit the volume of revolution questions? I mean, you know the formula. You integrate the function, you plug in the limits, but somehow the points just aren't there on your final score. Well, that loss of what Cambridge calls method marks is literally the ultimate system failure, and it's exactly what we're going to debug and fix today. We really need to stop looking at the final answer as the only goal. Instead, we've got to start looking at the entire process as a string of executable code that the examiner is grading line by line. All right, here is our boot sequence for today. First, core architecture. Second, the debugging matrix. Third, compiling the patch. Fourth, the beta testing arena. And finally, 5, code deployment. So, Module 1, core architecture. To really show you where things go wrong, let me introduce you to 2 of our junior developers. We've got Dev Alex and Dev Sam. Now, Alex is absolutely incredible at raw data inputs. Alex can look at a curve, intuitively know the exact integration steps, and just jump straight to the answer. But Alex causes massive memory leaks because of poor multi-stage analysis, basically skipping the core steps of written working on paper. Then we have Dev Sam. Sam is great at setting up logical loops and doing the actual math, but totally fails the strict syntax conventions. Sam's the one who forgets the pi in the volume formula, drops the dx or dy at the end of the integral, or leaves the final exact answer without stating the proper units. The kicker here? Both developers fail the firewall check, even if their underlying math intuition was totally spot on. And the reason both Alex and Sam fail is simply that they ignore the method mark strategy. The theoretical architecture of the 9709 system, it doesn't just want a standalone number at the bottom of the page. It specifically targets 3 distinct cognitive domains: knowledge and understanding, application, and analysis. So marks are actually awarded for your evidence-based reasoning. They want to see the precise limits of integration, the clear algebraic substitution, and exactly how you seamlessly connect this with other syllabus areas. Literally, the process is the product here. Moving on to Module 2, the debugging matrix. Now, what's really interesting about this is that we're looking at the ultimate algorithm for mathematical problem solving. It's the deconstruct, solve, evaluate framework. First up, you deconstruct. You have to identify your given equation, your exact axes of revolution, and your geometric limits. Second, you break it down into logical steps. Like, are you integrating with respect to x or y? Do you need to square the function before substituting it in? Third, you solve systematically, and I mean writing down every single mathematical manipulation. And finally, evaluate. Check for reasonableness. Seriously, if you calculate a negative volume, your system just crashed. There's no way around it. You need to justify your positive output and fix those bounds. All right, Module 3, compiling the patch. But hey, real quick, before we push this final patch to secure those maximal marks, I need you to optimize your system feed. Hit that subscribe button for Ace the Exams right now, and definitely turn on all notifications. We are deploying weekly system updates and hackathons exactly like this one, and trust me, you cannot afford to miss a single line of code. Go ahead and secure your access now. All right, let's get back to it and look at the patch. Think about what bad syntax looks like. It's a messy block of raw data. No contextual formula, missing integral signs, basically just a jumble of numbers. The examiner firewall is going to block that immediately. Now contrast that with a clean math syntax structure. This follows strict conventions. We're talking proper formatting, correct terminology, and clear annotation of the limits. It clearly states the formula first, inputs the expression, details the integration step by step, and explicitly links the evaluation back to the exact context of the question. That level of rigor is exactly what clears the system. Welcome to Module 4, the beta testing arena. Okay, initiating test 1. In the actual exam hall, you don't usually just get a neat, simple equation handed to you. You have to extract it from a complex diagram or some multi-part coordinate geometry scenario. Basically, you have roughly 60 seconds of processing time to execute a trend extraction. And the principal examiner reports heavily emphasize that mathematical interpretation is a critical professional skill here. You've got to extract the right coordinate intersections from the visual, interpret the bounds, and draw evidence-based conclusions about which area is actually rotating, all before you even write down a single integral sign. Now, initiating Test 2, the code review, and this brilliantly illustrates the top 3 system bugs that cause massive memory leaks, which we've pulled directly from the principal examiner reports. Bug number 1, formatting is omitted. Students literally just forget the constant pi, or they completely fail to square the y term inside the integral. Bug number 2, presentation checks are ignored. The algebra gets so incredibly messy that the examiner can't even follow the logical loop of the substitution. And bug number 3, the output isn't specific to the context given. If the question specifically asks for an exact volume in terms of pi, and you hand over a rounded decimal, yeah, your code fails the final check. And that brings us to the ultimate examiner alert. I really want to read this directly from the source code for you. Quote, candidates consistently confuse key terminology. Always define terms before using them in extended calculations, end quote. Listen, if you're doing a complex multi-part volume question that requires cross-topic connections, like maybe it mixes trigonometric identities with integration, you must explicitly state what you're substituting. You have to define your intermediate variables. Basically, show the examiner the clear blueprint of your code before you execute the integration. Let's track the chronological flow of time during the exam. I want you to think of your 15-minute time block for a high tariff volume question as a strict compile sequence. Minute 1, define your key variables and write down the base formula for rotation about the correct axis. By minute 5, you should extract your exact limits and intersection points from the diagrams. Minute 10, solve systematically. Apply all the correct calculus formats line by line, no skipping algebraic steps. And finally, minute 15, check your final volume for reasonableness. Is it positive? Are the exact units formatted right? That is your crucial final debug phase. And finally, Module 5, Code Deployment. So the really crucial point here is what we call the cheat sheet architecture. If you actually want to bypass the firewall and secure those A-level method marks, your mathematical working has to rely on 3 main pillars. First, precise definitions, meaning you state your volume formulas, geometric bounds, and variables crystal clear. Second, systematic analysis. Show every single line of your integration, your substitution, and your arithmetic clearly and logically. And third, cross-topic connections. You've got to be prepared to pull an algebraic rearrangement or trigonometry to simplify your function before you ever start integrating. Combine those, and that equation strictly equals maximum system marks. System bypassed. Mainframe hacked. You now have the exact syntax required to totally dominate the volume of revolution. But hey, remember, calculus isn't just about passing an exam. It is literally the source code of the physical world. From modeling planetary orbits to engineering the shape of a jet engine, mastering this means you're mastering the physics of reality itself. So what subject and level are you compiling next? Drop your current exam tier in the comments below right now so we can target our next system override. And of course, remember to subscribe to @AceTheExams, ring that bell, and I will see you in the next masterclass.